It's now time to derive the fundamental relationship involving the way the vapor pressure changes as a function of temperature and as a function of intermolecular forces. We've already seen what we expect for a result. We expect the result to do this. We expect at low temperature to have a relatively flat sort of change, and then as the temperature goes up, it increases exponentially. We also expect the thermodynamic value, the delta H of vaporization, to impact things. That the smaller the delta H of vaporization is, the more quickly as a function of temperature I see high vapor pressure. And if the delta H of vaporization is really large, then I would expect it to take longer, higher temperature, for me to start seeing substantial vapor. So that's the sort of result I want to see come out of this equation that I'm about to derive. So let's go ahead and get started. Realize that what makes this a physical equilibrium process is that when I have that surface, I have a gas molecule above the surface coming down onto the surface at exactly the same time that I have a gas molecule on the surface leaving, a liquid molecule on the surface leaving, that those processes are occurring such that the difference between the free energy of the gas and the free energy of the liquid is equal to zero. That's the definition of the physical equilibrium vapor pressure. Delta G vapor equals zero. Now, once I know that, I need to turn it into something which is useful for me in that it accounts for differences in pressure. This is a pressure-independent statement, but I can make it into a pressure-dependent statement if I want, and that pressure that I will be depending upon is the vapor pressure, by considering the following. So let's look at G of the gas and G of the liquid here. First of all, G of the liquid is actually going to be pressure independent. Because if you think about liquids, when you try to put a pressure onto a liquid, there is no significant change in the free energy. The volume doesn't change, and as a result, we can end up saying that G of the liquid is equal to G naught of the liquid. So this becomes pressure independent. We can't say that about a gas, though. Gases clearly have a change in their free energy as a function of the pressure, and so I need a correction factor for this. The correction factor we use is RT log P. So we substitute this correction factor in, and this allows me to identify a standard condition at 1 atmosphere and the correction if the pressure changes from that. So we can put those together into delta G vaporization from up here, and we end up having delta G of the gas plus its correction factor, and then the standard G for the liquid. When I rearrange those, I can now talk about a delta G for the free energy of the system plus its correction factor at standard conditions. So there's that value right there, a very key result. Delta G of vaporization under standard conditions is equal to RT log P. Now, if I want, I can turn this free energy change into something that I'm more comfortable with, and that's the heat of vaporization. I can do that by using the Gibbs free energy equation and recognizing that the change in entropy for gases under ideal conditions is going to be negligible. So isn't this kind of interesting? I've made 2 assumptions so far in this derivation that I'm showing you. One of the assumptions is that the liquid free energy is going to be pressure independent, and the other is that the change in entropy in ideal gases is going to be a constant. So as a result, I can ignore this, and when I do so, I end up having my delta G term be converted into a delta H term. Rearranging this, I come up with a very famous equation, which is the Clausius-Clapeyron expression. The Clausius-Clapeyron expression states that the vapor pressure of a gas is going to be equal to, oh, look at that. There's that exponential term I was talking about. The delta H of vaporization, once I have done away with accounting for delta S of vaporization, and there's my temperature term. How do these figure into this function that I'm showing you? It turns out that when I have e to a negative exponent, what I have in the numerator is a value where as it gets larger and larger and larger, the pressure gets smaller and smaller exponentially. And because my temperature is in the denominator, as that value gets larger and larger, the pressure gets larger and larger exponentially. This is my Clausius-Clapeyron equation, and this is what I will be using to demonstrate that kind of exponential growth we talked about.